Now I will start the third lecture of week 7 of this course. In this lecture, I will talk about other kinds of defects. We have already seen point defects in the last lecture. Now I will talk in a little bit more detail about the other kinds of defects, in particular line defects and planar defects. So, week 7 lecture 3 will be on line, planar and bulk defects in crystals. And again, let me emphasize that I will talk very briefly about these topics, and I encourage you to look at for a better understanding you should look at other sources. So, just to recall, we talked about different types of lattice imperfections in crystals. So, you could have point defects such as vacancies, interstitials, impurities and F centers, which we briefly looked at in the last class. Then there are line defects which we will look at today, disclinations and dislocations. Then there are planar defects, bulk defects and other lattice distortions are also possible. I will talk about line defects, planar defects and bulk defects in this class. So, the first kind of line defect I will talk about is called an edge dislocation. This is a kind of a dislocation, and I will talk about this because it is relatively easy to explain. Okay. So, now imagine that you are looking at a cross section of a crystal, and imagine that the atoms of the crystal have some regular arrangement. And I am just showing some regular arrangement, and you do not need to I am just showing a cross section. So, it just looks 2 dimensional, but it is really part of a 3 dimensional crystal, and imagine that this is a perfect crystal. Okay. So, this is a perfect crystal with atoms located at the lattice sites. Now, let us imagine that we do the following. We take out half a plane of atoms, okay, and let me just show it in a different color. Let us say you take out all these atoms that I have enclosed in green, and we imagine that we do it all the way to the, since the crystal extends, you take it all the way to the end of the crystal. And I call this a plane because this is actually here it just looks like a line of atoms, okay, but you should really imagine that the crystal is extending all the way outside the screen. So, it is really a plane. If you take all the atoms going directly out of the screen in this screen, okay, you will get a plane of atoms. Now, imagine that you just take out those plane of atoms, okay, and then what you do is now you rejoin the crystal. Okay, so, you rejoin the crystal so that away from that plane of atoms everything looks the same. So, these are the atoms above the plane, and let me just for convenience let me show these atoms in blue color. So, above the plane you have all the black atoms, and I am just this is just a cartoon representation. So, it's not going to be exactly correct, but it will give you the basic picture of this dislocation. Now, you have the blue atoms, and you have one blue atom missing here, okay, and because it is missing, you will just say that these atoms will come a little closer and they will, and I'll just show some of, I'll just show what kind of things you can. Now you get, now you see what I have done, okay. So you had this missing plane of atoms, I took this out, and then in order to fit the atoms, I moved all these atoms towards this side, moved these atoms a little bit towards this side, okay, and right at this point I just showed the missing atom, but you see that all the atoms near it have actually moved a little bit, okay. And now what we did, now if you put this extra plane, you will see something like this. Okay. So if you put the same number of atoms, you will see something like this. Okay. So this is that plane of, this is the half plane of atoms that we had taken out. Okay. So you take out a half plane of atoms and then you rejoin the crystal. Okay. So this is called an edge dislocation. Okay. And I'll show another picture which will be more in the context of the three dimensional picture of this edge dislocation. Okay. And let me again use the same colors, black to show the part where there is not been a dislocation. So So I am just showing part of the piece of the crystal. Okay. So this is a piece of a crystal, and this is the sort of the perfect part of the crystal, and what I imagine is that below I have the piece of the crystal where I removed one plane of atoms here, one whole plane of atoms in the crystal, and then I, after rejoining, okay, so what it looks like is okay. So you can imagine, you can see that this black plane of atoms, okay, it extends only up to here. In this side it is removed, and all the other planes extend all the way. Okay, and now that extra plane, I'll show it here. Okay, and this is actually quite relevant to the crystal. Okay, so this emphasizes that there is an extra plane of atoms, okay, that is due to this edge dislocation. Okay. The other thing that is emphasized by this is that when it comes to the surface, okay, there is an extra plane of atoms. So there will be this kind of step feature on the surface. Okay. So this edge dislocation has an extra plane of atoms. It's actually a half plane of atoms. I use the term half plane is used because you are taking only half of these atoms, and really it's a whole plane of atoms that goes all the way inside. Okay, it goes all the way through the crystal. So here we are only seeing a cross section, but the plane of atoms goes all the way through the crystal. It's half plane of atoms. Now there is a very important connection between the mechanical properties of the crystal and the presence of dislocations. Now if you apply a shear stress on the dislocation, a shear stress means you can think of it as applying a force in this direction and a force in this direction. Okay, so that will be the shear stress on the crystal. Okay, then this extra half plane of atoms, okay, can actually move. Okay, so then this missing set of atoms that are right here, okay, that can move. Okay, so it can this row of atoms can move here. Okay, then the missing plane comes here. This behavior is called slip behavior. Slip, this relates to the motion of the dislocation. And what will happen when you do this is that this dislocation will move along this direction. Okay, this dislocation will move this way. Okay. Now the dislocation is not just here. Actually, the dislocation corresponds to a line, okay, that goes all the way through the crystal. Okay, so the dislocation is characterized by this line, which is referred to as the dislocation line, and this dislocation line is it actually goes this way. Okay, so it is going through the crystal, and okay, so you have to really imagine that the crystal is infinite, and this is your dislocation line. Okay, and if it is a perfect edge dislocation, it will just be a straight line. Okay, it will be a straight line, and it will only terminate at the surface of the crystal. Okay, so it's a straight line for a perfect edge dislocation. Now the other kind of dislocation that is very common in materials is a screw dislocation. So screw dislocations can be visualized. Okay, they are also a kind of line defect, and it's easy to visualize them when you think about if you think in the following way. Okay, you imagine that you have a perfect crystal. Okay, and what you imagine is you imagine that you break this crystal. Okay, you cut this crystal along. So let me show it. So if you have a perfect piece of crystal, again I'll show the same kind of picture that we saw in the last in the discussion on the edge dislocation. Now what you imagine is you take this perfect crystal and you break it. Okay, so you cut it this way, cut it along here, and imagine that you cut it all the way across. So it goes. So you imagine that you cut it in this way. So you just make a cut in the crystal. Okay, and you can see that I am cutting it only halfway into the crystal. I am not cutting it all the way through. I am not going all the way to the other end of the crystal. Okay, so you imagine making this cut. Okay, so you just make a cut. Okay, then what you do after that is you imagine taking this this top half of the crystal. Okay, let me just extend this, and you just displace it. Okay, so you displace it in this direction. Let me use a different color. So that is displace by one lattice unit. Okay. And now after you displace by one lattice unit, then the new what you will see is that you will see it going like this. You will see these atoms coming like this and going like this. Okay, so you made the cut here, and after you displace, then these atoms will come this way. Okay. Now after the displacement, you can see that this row of atoms looks like this. So what you have done after displaced by one lattice unit, and you have rejoined it and rejoin. Okay. So after you do that, what you will find is you will find that this whole you will have something like this. Okay. Now what is to be noticed is that the dislocation line in this case. Okay. So this is the dislocation line. This is the dislocation line. Okay. And what you also see is that now when you shear the crystal, when you do the same thing that we said in the last time, you apply forces this way in the crystal. Okay, you shear it, then this dislocation will actually move in this direction. So the motion of the dislocation will actually be in this direction. So you really have to imagine that when you take this dislocation and start shearing it, then what will happen is that the direction of slip and the direction of motion will be this way. So instead of joining here, it will join here. Okay, and you will get you can imagine that you will get a longer this curved line will be longer. Okay, so the screw dislocation is another kind of dislocation, and both edge and screw dislocations okay, they can be visualized as extra or missing plane of atoms. You can think of it as an extra plane of atoms or a missing plane of atom. And extra, and I should emphasize that it is really a half plane. Okay, so these are really half planes. Okay, now both these dislocations. Okay, there are ways to actually characterize these dislocations. Okay, I won't get into that here. Okay, what I do want to say is that you can have what are called as mixed dislocations. okay, where basically the dislocation has partial edge and partial screw. Character, okay, and you can actually formally you can give a very precise meaning to this. Okay, so there is a precise definition which I won't talk about. Okay, so I'll just write it here. So there is a precise definition. This is based on the idea of a Burger's vector. Okay. So, and this will not be done in this lecture, okay, or in this course we won't be doing this. Okay. So, let me emphasize that I won't be talking about Burger's vectors, but for those who are interested, you can look how you characterize a dislocation using this concept of a Burger's vector. Okay. There is another kind of line defect which is less commonly known, which is called a disclination. Okay, so here there is a change in orientation. So this refers to a change in orientation. Okay, so you can think of it this way. If you have, for example, if you have I'll just show it in 2 dimensions. If you have a crystal that looks like this. A perfect square lattice. Now, let me imagine that I have a line here, and let me show it at some tilt. Okay. And so your crystal to one side of this line is oriented in this way. Okay. Now to the other side of the line, the orientation changes. Okay, and let us say that the crystal is again the same lattice, but at a different orientation. So, for example, you could have something like so. It is the same structure, but at a different orientation. Okay, then this would be called a disclination. Okay, so such a defect is referred to as a disclination. Okay, again it is what is very crucial to remember is that this lattice constant and this lattice constant are the same. Okay, it is the same lattice. Okay, it is just that the orientation is changed. Okay, so it is just a change in the orientation across this line. Then this line is referred to as a disclination line. Okay. So, disclinations have now notice that if you look at these distances will actually be larger than the lattice spacing. So if this lattice spacing is A, then the spacing between atoms on this line will actually be greater than A. Okay. So, but in this crystal, okay, these again are this spacing is again A. Okay. So, there has to be some matching of matching of these atoms here. Okay, and that is what leads to this disclination. Okay. So, disclinations and dislocations are the kind of are the most common line defects that you have. Okay, but you can also have other defects. Now, line defects have a very important consequence on the mechanical properties of crystals. So what we saw is that when you if you take a crystal and you imagine that you are taking this crystal and you are shearing it. So, shearing it, you can I will just show it this way, that this is, imagine that this is a 3-dimensional crystal and you apply a shear force. Okay. So, shear force means you apply one force in this direction and one force in this direction, equal and opposite. Okay. And what this will do is it will tend to deform the crystal, it will tend to cause the crystal to be deformed. Okay. And now so the question is, how, if you now take out this shear. Okay. So, now if you remove the shear, okay, so you remove shear, okay, then does the crystal come back to exactly the initial configuration? Okay. So, does it come back to, if you remove it, there are two possibilities. Okay. So, either this is exactly the same as starting configuration, okay, that means it is exactly same as this configuration. Okay. So, if this, so you do a shear and then you remove the shear, and then if it comes back exactly to what it started with, okay, then we refer to this as elastic deformation. Okay. And the other case, when it is different from the then we call it a plastic deformation. Okay. So, if this configuration after you remove the shear is not the same as what you started with, okay, then we say that the crystal has undergone a plastic deformation. Okay. And typically most crystals, okay, will behave elastically for small deformation. Okay. So, small deformations is usually elastic. Okay. In this case, the atoms just move a little bit from their lattice positions and then they return to. So, atoms have small lattice displacements. Okay, that means they are very close to where they were in the lattice, but just small displacement of atoms. Okay, so this refers to the elastic deformation. Now, if you make the deformation too large, okay, then the atoms will actually slip. This is actually a crack, okay, or the mechanical term is yield. Okay, so for larger deformations. So, when the deformation is too large, then there will be a slip, it will crack or yield. Okay. So, if you have a perfect crystal, if you have a perfect crystal, then this is what you can expect. Okay. Now if there are dislocations, so presence of dislocations makes slip easier. Okay. So, if your crystal has these dislocations, then it is actually easier to do this slip and these larger deformations in this. So, plastic deformation, okay, and plastic deformation becomes easier. Okay, so plastic deformations are related to dislocation motion. Okay, so this is really related to motion of dislocations. And you can see that when you move when you apply shear, let us just go back to the previous slide where we showed the plastic deformation. Okay, so when you apply this plastic deformation, this dislocation will move, and once it moves, if you take out this deformation, the dislocation is not going to move back. Okay, so these are permanent deformations in the material. Okay. So the presence of dislocations actually makes slip a lot easier. Okay, and this is a very it's historically a very important observation. Okay, that this was historically it's a landmark observation. It's a landmark observation, or I will just say it's a landmark observation which so real crystals have dislocations. So what I mean is that the theoretically calculated strength of a crystal, okay, it was much larger than what was experimentally observed, and therefore people concluded that real crystals have dislocations. Okay, and this basically had to do with mechanical experiments where they checked at what shear stress the crystal starts showing yield or large deformation. So when does it start slipping? Okay, and clearly if you had a crystal with more dislocations, it would slip easier, okay, than a crystal without any dislocations. Okay, and so when the properties of crystals were seen, it was observed that the theoretically calculated strength was much larger. And when I say much larger, it's like from about 10⁴ times larger than what was seen experimentally. Okay, so therefore it was concluded that it was actually postulated that real crystals should have these line defects, and then soon enough they were actually observed in real crystals. So again I mentioned briefly about elasticity and plasticity. Okay, so what we say is you can show this in some sort of a graph. Okay, what is typically shown is something like a stress versus strain curve. Okay, and strain versus stress. So if you take any typical material, okay, stress and strain are proportional to each other. This is the linear elastic regime. Okay, and at some point the crystal will start undergoing plastic deformation. Okay, and when it undergoes plastic deformation, so in this elastic region, if you take out the stress, it will come back to the unstrained configuration. Okay, and this is the plastic deformation. Okay. You can have other behaviors also, but a typical behavior will have an elastic region and a plastic region. Okay. Now I should emphasize that strain refers to deformation. That means how much you can deform the crystal. Deformation okay, and stress refers to the applied force. Okay. Formally, it is related to the applied force per unit area, okay, and strain is related to the deformation per unit length. Okay, but I just want to emphasize that strain is related to deformation, stress is related to the applied force. Okay. So once it starts plastically deforming, a very small increase in applied force can lead to a large change in strain. Now, let me also briefly mention some other type of defects that are possible. Okay. So, I will talk about planar defects. Such as stacking faults. Now, so stacking faults and grain boundaries are kind of planar defects, and I will just illustrate the idea of a stacking fault using the idea of a cubic close packed. So, cubic close packed structure, okay, and you can think of this as the 1-1-1 direction of an FCC. So, that is a cubic close packed structure. So in this you can think of this as in the following way. You can imagine that there is a hexagonal lattice. Okay, so this is the z equal to 0 layer. Okay, let me mention here that this is FCC, and it is actually the 1-1-1 Miller plane. Okay, I haven't explicitly discussed Miller planes, but we will see that. So, this is the first layer, this is z equal to 0, and then the next layer, okay, is located here, or let me call this layer A, and the next layer is right at the centroid of this triangles, at the centroid of these triangles, and this is called the B layer. Okay, and that you assume, I mean you can really think of these as spheres, okay, that are touching each other. So if you imagine that one sphere is like this, and another, these three spheres they pack in this manner, okay, and the next layer is right in this region. Okay, so that is the B layer. Okay, and the C layer, okay, in this cubic close packed, there is a C layer which is actually in these positions. These positions. Okay, it is in the it is a centroid of the other triangles. So this is a standard cubic close packed structure, okay, and so the C would be something like this. Okay, and so this cubic close packed structure, it looks like A, B, C, A, B, C, A, B, C. Let me write the B, C, B, Okay, so this is the as you go from the bottom to the top. So in this direction you are going from the bottom to the top, or vice versa, you can go the other way also. Okay. So it is referred to as an ABC type stacking. Okay. And now you can see what kind of stacking faults can be there, and to understand the stacking faults we will just look at these at this part, okay, where we show the ABC. Okay. So a stacking fault could be something like this. So you have ABC, okay, and then what you have is here you have CBA, okay. In the sense you have the ABC stacking, but in the opposite direction, in this direction. So here the ABC was in this direction, here the ABC is in this direction, and right at their boundary you have a stacking fault. So this would be a stacking fault. Okay. So right here you have a change in the orientation of the crystal. So on one side it is going in this direction, and the other side the ABC is stacking in this direction. Okay, and you have the stacking fault here. So this is a very classic stacking fault. Similarly, for the hexagonal close packed, hexagonal close packed is also a close packed structure. So HCP has AB stacking. Okay. Okay, so it has AB stacking. Okay. Now in this case you can't really have a stacking fault. Okay, you cannot have I mean you cannot really have a change in the direction. Okay, because I mean A and B alternate each other. Okay, but when you have ABC you can have a change in direction. Okay, so the stacking direction of this side of the crystal is different from the stacking direction of this side of the crystal. Okay, this is possible in structures like cubic close packed or more complicated structures. And this is a planar defect because actually this extends through this whole layer. Okay, I mean this is an ABC. ABC actually represents A represents one whole layer. Similarly, B represents one whole plane of atoms. C also represents a whole plane of atoms. Okay, so ABC actually represents a whole layer. So this is actually the stacking fault is a planar defect. It's a whole plane of defective atoms. Okay. So the other example of a planar defect, and I won't talk too much about this. This is a grain boundary. Okay, grain boundary is where the crystal is essentially growing in a different direction. Okay, and you can have I mean you can have one grain of the crystal this way. Okay, and you could have, let us say, another grain of the crystal that is let me just show it growing in some other direction. Okay, just to illustrate the point, and then we'll join them where they so I am just showing two crystals that are growing in two different directions. Okay, they are the same crystal. Okay, you have to imagine that they are the same crystal, and this would be a grain boundary. Okay, so you have in this grain is growing in this direction, this grain is growing in this direction. Okay, now grain boundaries are actually, they can be arbitrary directions. Okay, so grains are single perfect crystals. Okay. And this grains can be oriented arbitrarily. Okay, so they can be oriented arbitrarily. Okay. And I will just make this statement. Okay, again you can look up for more information, because I won't be talking about this more. Okay, but a low angle grain boundary can be viewed as is equivalent to a row of disclinations. Remember, a disclination is a line defect, okay, whereas a grain boundary is a planar defect. Okay, and a low angle grain boundary can actually be viewed as a row of disclinations. Okay, again I won't talk too much about this. Okay, but this is some information that you might find useful. Okay, so that's how much I want to say about planar defects. Now I'll just say very briefly about bulk defects, and again I am going to be very brief. Okay, and now the two kinds of defects are I'll talk about are voids and precipitates. Okay, and a void is basically a collection of vacancies. Okay, so if you have a large cluster of vacancies, okay, come together, you form a void. Okay, and this can also lead to cracks in the crystal. Okay, and precipitate is inclusion of some other material you can also have, I mean, inclusion of some other material, and let me underline the word other. Okay, it need not be a different material altogether, it could just be a material that is treated differently. Okay, so for example, you could heat one part of the material, okay, and now that part of the material is hotter than the others. Okay, and that would be an inclusion or a precipitate. So if you look at a crystal, okay, the voids in the crystal would be like these regions where there is no crystal. Okay, so if all this is the crystal, all this is a region of the crystal, then the voids would typically look like this. So this is a fairly large. Okay, so what should be kept in mind is that compared to an individual vacancy refers to one missing atom. Okay, whereas a void is a very large collection of atoms. So typically voids are large, of the order of nanometers and more. Okay, so nanometer size, and then inclusion would look let me take the very similar configuration. So you have the perfect crystal all around, but somewhere you have some inclusion of some other material. Okay. Now in these two figures you can see what will happen. Now whether you have a void or an inclusion, okay, the crystal, the remaining part of the crystal will experience some forces on it, okay, and more precisely it will experience certain strains on it, okay. So either due to the void or the inclusion, either there will be some sort of forces on it, okay, some sort of forces on the surrounding crystal due to the voids and the inclusion, okay. And what is to be noted is that the voids and the precipitates will have very different effects. I mean the forces due to a precipitate will be very different than due to a void, okay, and these forces will depend on the precipitate also, okay. And so the mechanical properties of the crystal are greatly affected by the presence of voids and precipitates, okay. And so this basically concludes the discussion on the line defects, planar defects and bulk defects. I will just mention one more small point, okay, and this actually refers to non-stoichiometric compositions, okay. And all I am saying is that if you have a crystal, let us say of the form A, B, X, okay, so this is overall composition, okay. And now let us say A and B are very similar in size, let us say A and B are very similar in size, okay. So and let us say they form a very almost their lattices are identical, okay. So then your crystal would look like some A and some B's, okay. And what you can see now is that this is a completely disordered, this is an example of a disordered solid solution. So this is a disordered solid solution or a disordered alloy, okay. So what you mean is that A and B, there is no order, so each site is either occupied by A or B, okay. So each site is either occupied by A or B, and such that the overall fraction is overall composition is A times B to the X, okay. So here is a case of a crystal which is characterized by a fractional occupancy, okay. So this has the concept of fractional occupancy, okay. And again this is something that we will see when we are discussing alloys more, okay, when we are discussing alloys and solid solutions. But you can imagine that instead of this you could have A and B form a very regular pattern, okay, where instead of forming this fractional occupancy kind of structure, you could have something like a regular structure like the zinc blende or the sodium chloride or the cesium chloride, okay. Those are not fractional occupancy compounds, okay, those are regular compounds, Okay, but this is an example of a crystal which is characterized by this fractional occupancy. Okay. So, I will conclude this lecture, and with this I will conclude the discussion on line, planar and bulk defects. In the next lecture we look a little bit at the thermodynamics of defect formation. Thank you.